Hey everyone, this is Team 7, and our Senior Design 2 project was to make a sousaphone or a musical Tesla coil.
The objective motivations of this project is to make a Tesla coil and play music through electrical discharges. And that will communicate with the microcontroller and change the song that's being played. The motivation behind our design was to create an entertaining device using power electronics. A Tesla coil is comprised of two circuits, primary and secondary. They form two capacitance and inductance banks where voltage and current are stored. They are weakly coupled by a low K value. The goal is to match the resonant frequency of both circuits, and they must be close to each other in order to transfer power. The current flowing in the primary transfers energy to the secondary, creating high voltages and discharging through the secondary in lightning-like charges.
Our goal was to build two large Tesla coils, approximately 2 to 3 feet tall, 5 to 6 inches wide, with around 1,000 turns. We were to step up from 120 volts to a higher voltage of a maximum of 10 kilovolts using a transformer, 1 megahertz minimum frequency, and design an app in which we can pick a song that will play directly onto the coil.
This is a block diagram that describes the basic functionality of how our software interacts with our hardware. The user input is handled by the Android application, which sends a signal to the Raspberry Pi. The Pi then receives that signal and either responds to the app or sends the audio output to the electronics. The electronics convey this output to the Tesla coil.
The hardware requirements for our circuit were a 70-volt AC 5-amp power inverter circuit, around 1.1 megahertz secondary resonant frequency, a secondary coil wire gauge of 32 American wire gauge, primary coil wire gauge of 20 American wire gauge, and power consumption of 500 to 600 watts. For our hardware design, we utilized programs such as Java TC to calculate primary and secondary coil parameters such as the resonant frequency, and modeled individual elements of the circuit on breadboard to ensure they were working properly. For troubleshooting, we simulated the circuits on LT-Spice to confirm theoretical values and behaviors.
This is a schematic of the final circuit that was used. On the right, we have the power inverter and the secondary coil. And on the top, we have the logic power supply. And bottom left, we have the inverter and the driver power circuit. And we will go more into depth into these in a second. So this is the IC power circuit. It's essentially just a power supply for the all the chips on the circuit. We use two regulators, 7812 and 7805, to power the logic with 12 volts and 5 volts respectively. The capacitors are there just to smooth out the waveform, and there's a bridge rectifier to take the AC voltage to DC. This is the interrupter and the driver part of the circuit. So the left part is the interrupter. This takes the audio input and essentially modulates it using a PWM. And that goes into the driver part of the circuit, which uses a 74HC14, which is configured in a Schmidt-Trigger oscillator circuit. So this is what we actually tune to get our primary resonant frequency. We tune it to the secondary, and it oscillates at the secondary. This is really confusing. I'm gonna have to redo this one. I'm just gonna start over. So on the left, we have the inverter circuit. So the output of this is basically a PWM or essentially an FM signal. And that goes into the driver part of the circuit, which is composed of a UCC 27524, which is a MOSFET gate driver, just controls the voltage on the MOSFET. And below that, we have a 74HC14, which is a Schmidt-Trigger oscillator. So the Schmidt-Trigger oscillator is tuned to the secondary resonant frequency. And that turns on the gate driver above it to control how fast the MOSFET turns off and on. And this basically is how we achieve resonance in the circuit. And the input from the 555 can basically modulate the driver circuit and turn it off and on. So you can either get better power consumption or you can modulate it to get some sort of audio output. This is the power inverter and coil part of the circuit. So the secondary is obviously on the left, and on the right, I mean, well, I'm gonna restart that because that sounds stupid. This is the power inverter and coil part of the circuit. So the secondary is on the right, and the power inverter and primary is on the left. So we have mains AC coming in, and that's rectified to DC. And then we have a really large high voltage capacitor, 1000 microfarads, 470 microfarads, to basically smooth this out so you get a very straight DC line. And then that goes into the primary winding, which is also connected to the MOSFET, which that's what's being switched on by the driving part of the circuit. And then we have two TVS diodes, these are just for protection, so we don't so any voltage transients don't destroy any components in the circuit. And then we have a resonant capacitor, so that's how we get the LC circuit on the primary. And then the secondary, we said it was an LC circuit, but the capacitance is just with the secondary winding to ground.
All right, so now we'll move on to a demo of our coil operating. So in this video, the coil is connected to the driving circuit, and instead of an audio player, we have a function generator connected to the audio input. And as we increase or just change the frequency, you can hear the pitch shift. So as the frequency goes up from about 1 kilohertz, you can hear the pitch get increasingly higher. And as we go back down, you can also hear it getting lower.
Are you recording this sound?
Yep.
Are you recording this as well?
Yep. And then maybe back down.
This is about 10K.
Okay.
Crossing 8K. 7K. 6K. 5K. 4K. 3K. 2K. 1K.
The software requirements for our project was to develop a media player app using Android Studio and to use Python on the Raspberry Pi to establish Bluetooth connectivity between the two devices using RF-COM protocol. The methodology behind the software development was to first develop basic Bluetooth functionality on both the Raspberry Pi and the app, and then establish a Bluetooth socket between the devices for data transmission of strings. We then designed a basic UI that structures the data transmission and encompasses the desired functionality. For the app UI, we kept it simple. At the top is a select device button, which is used to pair the media player app to the Raspberry Pi. Below that, we have an update list button, which retrieves the newest playlist from the Raspberry Pi. We then have a simple play pause button, and then a scrollable and clickable song list.
For the design of the Android application, we imported the Java Bluetooth package, which gave us the identifiers for Bluetooth adapter, socket, and the corresponding input and output streams. This was pretty essential when it came to facilitating the communication between the app and the Raspberry Pi. We also used Java libraries for text file manipulation, which was corresponding to our song list, and used multiple toasts to give messages to the user of what was loud and what wasn't. The main code was broken into 3 activities. One was for handling the UI interaction between the user and the app itself. Another was for the recycler view or the list of songs, and then another to handle the Bluetooth functions and classes between them. For the functionality of the app, we make sure a device is paired to the phone, and once a device is paired, a Bluetooth socket is created between it, where it waits for a user input, which could be one of 3 things. If it is wanting to update the song list, it sends a signal to the Raspberry Pi and then receives the song title to be updated in the list. If it wants to pause or play the current song, it will go ahead and send that signal to the Raspberry Pi. If it wants to play any song title that it's currently shown, it will just send that song title to the Raspberry Pi. In the event that the app is closed, the Bluetooth socket will also close and the app.
For the Raspberry Pi, we decided to use the Python programming language. This is because Python has a vast selection of libraries and is a high-level interpreted language. We use 4 main libraries for this project. The first 2 are for Bluetooth and socket exchanges. This allows us to create a Bluetooth socket and bind it to the Bluetooth port on the Pi. We also can create a Bluetooth service that is bound to a send and receive UUID. The Pi then waits for a Bluetooth connection and enters a while loop to send and receive data. The OS library stands for operating system. This allows us to check for playlist updates and send that data to the app. There is a directory on the Pi that holds each song. When an update is requested, we create and populate a text file with every file name in that directory. This text file is then compared to an old file, and any differences are sent to the app for an update. The old file is then replaced with the new one so that we can always keep an updated list on the Pi. Pygame is a library that is mainly used for making video games in Python, which means that it has built-in classes for music. This allows us to play, pause, and manipulate the music in many ways. Dot wave files are used for the audio output due to needing a lower computation power than MP3. This helps with audio distortion. This is a functionality flowchart for the Raspberry Pi. When the code runs, it listens for a connection. If a device is paired, it accepts the connection and creates the Bluetooth socket. It then enters a while loop that continuously checks for data from the app. If the app wants an updated song list, the Pi uses the OS library as previously stated and sends an update. If the app wants to play or pause a song, the Pi plays or pauses the current song. If no song is playing, it plays the first song in the playlist. Any other data is received as a song title. If the song title is already playing, it restarts. If the song title is not already playing, or if a different song is playing, the new song is immediately played. If no signal is received in 5 minutes, the Bluetooth socket is closed and the program stops. So this is our Python code for our Raspberry Pi. As you can see, it runs Pygame, and it's waiting for a connection from the phone. And so on the phone, we can select the device as Raspberry Pi selected, connection successful, and then it accepts the connection from the phone. So now, from the phone, we can pick a song in the list and play it. So let's pick Sail, for example, and it's playing. So now if we want to pause the song, we can pause it. And it shows us a message here that says we paused it. We can play it. Plays it again. If we want to switch songs, we can do this. Alright. Now, as this is playing, we can add a song to our list, and we can update the list, and it puts that song here, and now we can play it.
For our performance analysis and final results, the final circuit arcs, but still does not play music. Additionally, the arcs are a little bit smaller than expected because we can't input high enough voltages due to some noise issues with the circuit. However, the circuit is capable of playing different tones at certain frequencies, and this is done by connecting a function generator instead of a audio player and just changing the frequency on the generator. You can hear it pitch up and pitch down. However, it has problems at lower frequencies. Again, we think this is due to some sort of noise in the circuit. Anything below a kilohertz is really hard to hear. Additionally, our gate driver IC has some output issues. One of the pin outputs works as expected, but another one is severely attenuated. We also have some PCB design issues. The way the PCB was routed, there are some issues with attaching heat sinks, so some components get a little bit warmer, but we were able to sort of fix the problem, but the heat sinks aren't large enough to dissipate enough power. And since the routing on the PCB isn't optimal, there are some potential crosstalk and induction problems, which is a big source of noise in this circuit. And this might require isolation to also fix these problems on the side of the gate driver and the driver circuit.
For the performance analysis of the software, the final design completed all software requirements, but something that we would improve with this project would be to add a lookup function with a song library like Spotify, but this would require licensing and more time.
Some strengths on the hardware side of our project include that the final coil was able to arc and change output frequency using a function generator as input. It had an adequate volume for audio output, and the logic power supply using the voltage regulators was stable and reliable. Some weaknesses on the hardware side of our project include that the final circuit was unable to play music from the audio input, difficulty installing large enough heat sinks in the PCB layout to dissipate enough heat. Time spent troubleshooting limited our time to construct a second coil as we had planned to do. We weren't able to operate at higher voltages due to the noise in the circuit.
A strength of our software is that it's a concurrent design. The Raspberry Pi can do multiple processes at once due to our signal processing technique. The Pi only receives 1 unit of data at a time from the app, and then it takes that data, reacts to it, and then waits for a new signal. These actions that occur after receiving the data run in the background as the Pi listens for new input. This allows us to play a song and receive signals for new songs, library updates or pausing and playing the song while a song is actively running.
As previously mentioned, one of the weaknesses for our software side of things was that it became relatively tedious to update the playlist of songs. Whenever we wanted to do this, a song had to be manually imported onto the Raspberry Pi, as well as updated in the song list. A solution for this would to be receive the API, which is the Application Program Interfacing certification, and use Spotify for song lookup and loading.
So in conclusion, when making a Tesla coil, there are several intricate variables to consider, like the inductance of the primary and secondary or their coupling coefficient that need to be fine-tuned for it to function